Welcome everyone for the first ITC lunch of the academic year. We've had a very productive summer, and as of today, we should mention first that as Charles just sent a message around the CFA that the Breakthrough Prize in Fundamental Physics was awarded to the Event Horizon Telescope collaboration. So let's all acknowledge that, and we definitely agree that it's a fundamental physics discovery and at the same time a breakthrough in our understanding of black holes. And we're very glad to host the Event Horizon Telescope team at the Black Hole Initiative, 20 Garden Street, which is not very far. Also, I would like to use this opportunity to welcome the new postdocs that are that joined us. But before that, I wanted to thank Erin Kara for sponsoring the ITC lunch this academic year. It's for the third year in a row, and he also sponsors our prize for best PhD in theoretical astrophysics every year. So thank you, Eric, for doing that. We'll have a photo taken of everyone. All affiliates of the ITC are invited to come out after the lunch. We'll be out there. Mark arranged for a beautiful weather, so thank you, Mark. And I should also mention that the ITC Lunch Series is being organized this year by Paul Duffel. He's sitting at the back there, and if you have suggestions, don't hesitate to contact him. So the new postdocs that are joining us, let me mention those that should be in attendance here. First, Matthew Liska is over there. He got his PhD from the University of Amsterdam, and he's joining us as a John Harvard Fellow, which is a very prestigious fellowship at the Faculty of Science here at Harvard. And he's also an ITC Fellow. And also I would like to mention Angelo Riccardi, who should be here. Yeah, he's there. He got his PhD. Got his PhD from Yale in this year, and he's joining us as an ITC Fellow and an NSF Higher Fellow with Ramesh Naran. Vadim Semenov is over there. Vadim graduated from the University of Chicago, and he's joining us as a Hubble Fellow and then an ITC Fellow. And Brian Terrazas, Brian graduated from the University of Michigan, and he's joining us as a Harvard Future Faculty Leaders Fellow, which is a very prestigious fellowship again that we have here at Harvard. Congratulations, Brian. There are a couple of new postdocs that are not in attendance. I would like to mention them as well. No need to clap because they're not here. Carl Rodriguez got his PhD from Northwestern in 2016. He was a Pappalardo Fellow at MIT between 2016 and 2019. And he's joining us as an ITC Fellow for 1 year because he already has accepted a faculty position in Pittsburgh. He's traveling this week, so that's why he's not here. And then Matthew Smith got his PhD at the University of Cambridge, and he's joining us as Simon's Fellow, and later on as a postdoc fellow with Lars Hernquist. He will come here in mid-October. And then let's see, let me mention a few of the postdocs that left the ITC. One of them left just to the upper floor, and she's here, Antonia Ofrovich. Yes, she's right here. And she will become a Sagan Fellow at SSP. John Forbes went as a fellow at the Flatiron, at the Center for Computational Astrophysics at Flatiron in New York City. Manasvi Lingam became an assistant professor at Florida Tech. Mohammad Safarzadeh went as a postdoc fellow to UC Santa Cruz. Anna Ijas became the Lisa Meitner Research Group Leader at the Max Planck Institute for Gravitational Physics. And this is a permanent associate professor equivalent position. And then Benedict Dimmer will be an Einstein Fellow at the University of Maryland starting in October. And then a year later will become an assistant professor. So these are all the announcements. We have an exciting program of 4 speakers, but just before the 4 of them speak, I wanted a visitor that we have, Karan Jani, who is visiting us from Vanderbilt. He actually gave a talk at the physics department, and he will summarize it with one slide. I asked him to summarize it. He's a member of both the LIGO and the Lisa teams for gravitational waves, and also was chosen as the 30 favorites under the age of 30 by Forbes magazine recently. But Karan, before you start speaking, I'll mention the other 4 talks and then we move straight to them. The 4 talks we have are the first by Matthew Liska, that I mentioned before. He will talk about exploring black holes in unexplored regimes using GRMHD simulations. Then we'll hear from Mercedes Lopez-Morales, who gave an excellent ITC colloquium, and she will speak about the access, the power of low-resolution exoplanet atmospheres, observations from the ground. And that will be followed by Erin Kara from MIT, that will give the CFA colloquium. I hope she's here. Here she is. She just came here from MIT after giving a class there in the morning. Yeah. And she will talk about the radical transformation of bright nearby AGN. And finally, we'll hear from Joel Leja, who is a student here. Where is he? Of course, the and he will talk about an older, more quiescent universe from the Panchromatic galaxy SED. From a Panchromatic galaxy SED fitting. So we'll start with Karan, one slide, and then we move on to the 4th.
Well, thank you, Avi, everyone, for having me. It's very brief. I was visiting the particle physics group here where I gave this talk to a lot of string theorists, and Avi recommended that many people here would rather be interested on what the intermediate mass black holes are in gravitational waves, specifically LIGO. This is the LIGO Livingston Observatory, where I've spent a lot of time as a graduate student at this site. This is the most sensitive gravitational wave detector we have currently on Earth. Just for scale, this is where we park a regular car, and you can't even see the whole 4-kilometer arm. So this is the Livingston Observatory. Now quickly, when I started this study as a graduate student, a lot of people in the field were pessimists that whether we even have black holes that we will see in LIGO that are really sort of massive. We'll really see only binary neutron star. But we had a fair understanding that the space of black hole is divided really in astrophysical sense in 3 categories. You could have stellar black holes formed from supernovae. You could have the supermassive black hole, like this famous Event Horizon team's picture. But between these 2, there remains some sort of a mass gap, what we call intermediate mass black holes. There has been evidence from electromagnetic observations, nearby observations relatively, but we are unable to can still pinpoint and know how this formation happens, what is the exact mass range. So their detection still remains unambiguous. And this is where most of the work that I do in LIGO will look for gravitational waves from intermediate mass black holes that collide create gravitational waves. And it just so happens that the LIGO detector right now, which is the sort of red contour you see, the scale here is mass in source frame, log scale, and the redshift. One of the best things LIGO detector by itself, just because of its design, can see is an intermediate mass black hole collisions of around 200 solar mass. In fact, we have searched for all possible systems at most up to 800 solar mass. We have not found any intermediate mass black holes in the last 2 years we have searched. The third observing run started only this April, and we are still ongoing looking for it. But what has been truly surprising is just within this observational time, we already have found black holes that almost put bounds on what the pair instability gap could be, right? We have black holes even higher than that. In fact, we have found a marginal trigger. We cannot claim that as a detection just for the, the threshold we keep in LIGO, but we have started seeing some sort of a mysterious population popping even at about 170 solar masses. This is just the start in gravitational wave astronomy. In future, we are going to have another detector, hopefully, going to come in the US, which is a Cosmic Explorer. It's a 40 by 40 kilometer version of LIGO, provided it gets funded in time. That would come in mid-2030s. And there is an Einstein telescope, a similar triangular design, which is going to be in Europe. And then just from gravitational wave, and again, what we detect every time, just the constraint on mass is so powerful, and we know the gravitational wave came from the event, just outside the boundaries of event horizon. Hence, we can very strongly constrain that these are actually black hole matrix. We could probe almost, this half of the space of what an intermediate mass black holes would be. I promise only one slide, so this is just a continuing that slide. And if in case the next mission that I work on more these days is this laser interferometer space antenna. It's a joint NASA European Space Agency mission. It's not going to happen in the lifetime of a grad student right now, but it is going to happen in our lifetime. Right? This mission is going to hopefully launch by 2034, and then you have this whole new space, right? All possible intermediate mass black hole that exists pretty much in the whole universe, because we can see redshift thousands. And this is a detection threshold. Any system binary black hole merger in this blue curve, we can see it. And just in case we are not optimistic enough, we've also proposed a mission for 2050. We just sent a proposal to the European Space Agency, which would be able to cover even further black hole range. So we are really, it's very similar to how the exoplanet search is, that we want to cover as much space as we can. Future telescopes are going to do it. But that's all I'm going to leave it, and this is what the current status is, however. This is what our O3 is, and thank you. Okay, thank you.
Very nice talk. Yeah, so hello everyone. I'm new here. I just arrived like 3 days ago. But before that I was a graduate student at the University of Amsterdam. There I've studied together with my supervisors, Michiel van der Klis, Sarah Marr, Coffin, Adam Ingram, let's say accretion disks and jets around all masses of black holes. For that I also collaborated with Tchakovskoy, who is like now I think almost 2 years a professor at Northwestern University. So what do I study? I study mostly, let's say, black holes of all mass ranges. You have, of course, the X-ray binaries, which form accretion disks from a binary partner. Same process applies for supermassive black holes. Of course, when you have an accretion disk and you have some kind of poloidomagnetic field, this accretion disk generates turbulence. The turbulence causes viscosity, and this viscosity drags all the material in together with the poloidomagnetic field. The black hole is spinning, then a jet gets launched, and this jet is really important, I think, to not only understand black holes, but also understand how, for example, galaxies grow, how the star formation rate changes as a function of, for example, black hole mass and the black hole spin. And for that, I think the most efficient and best way to do it is using GRMHD simulations, because you need to include general relativity, you need to include the magnetic fields, you need to include you need to include the laws of plasma physics, and GRMHD is kind of the method that can model all of these effects together. Here is such a simulation of an accretion disk and a jet. I'm just doing nothing. I just insert an accretion disk with a magnetic field, and immediately turbulence develops, and in yellow, that's the jet, it gets automatically launched. There is no, let's say, trickery involved in generating the jet. GRMHD simulations have been very successful in modeling, for example, M87 in the EHD collaboration, which is, let's say, a low luminosity black hole compared to the Eddington accretion rate. There has great progress been achieved. However, now I'm going to be a little bit critical. While most, like maybe 99% of the black holes are indeed kind of these low luminosity black holes, some black holes can be very luminous, still sub-Eddington, but luminous. And during these luminous phases, the accretion rate can be like a million times higher. So if you look at the black hole distribution, here I show the black hole distribution kind of that most black holes are at low luminosity. But if you multiply it by the energy output, then we see that actually most energy is released during in the high luminosity phase, and there are actually very few simulations that capture these black holes, and that's actually a problem. Why is that? Why isn't it easy to simulate luminous black holes? Because non-luminous black holes, they are inefficient in radiating energy. They cannot cool, and if they cannot cool, then they just puff up, become thick, and for a thick accretion disk, you need a much lower resolution. For a thin accretion disk, you need to focus the resolution really well on the disk. Plus, of course, there is no reason to believe accretion disks and black holes would be aligned with its extra complexity. If we would want to do it with traditional codes, then likely we would need to buy like a $10 billion supercomputer and have it running for like 2 years if we would want to simulate something like that. But during my PhD, I've developed a code that can do it. And it's not one trick that I can do it. I've started kind of working on a publicly available code, which is start harm 2D. I've optimized it, added new solvers, made everything better, and in various ways I factorized it. On CPUs you have multiple cores, but also each core can, for example, process like 8 floats or 4 doubles in parallel, and factorization can help you achieve pretty decent speedups. Then I've also made GPU versions. GPUs are much faster than CPUs. If you compare like a latest generation Skylake CPU versus a latest generation V100 GPU, then you get typically speedup of like a factor of 5. But most of the speedup actually comes through my adaptive mesh refinement toolkit. This toolkit allows me to focus the resolution where it's important. This is just, a placeholder, move it's nothing super fancy or physical. but I show I can focus the resolution where I want. Also, each block can be, so each of these white squares can be evolved at a different time step. Plus, I'm willing to talk about, I use spherical coordinates, but I think I have the most advanced spherical grid that has been developed, because spherical grids slow down simulations. Mine doesn't. I'm not going to talk about it. And all of this is scalable to DOE Summit, which is the largest machine in the world. So one simulation I've run, I started with a thin accretion disk around a rapidly spinning black hole. The disk and the black hole spin axis were tilted. Black hole spin axis points up. The disk is tilted, and I started to run it. Immediately, we just see a disk rotating around the black hole, but if you look, the disk tears apart in actually two disks, which is really interesting, because in observations we know there are, for example, quasi-periodic oscillations, and there have been simulations of precessing accretion disks, but all of these simulations started with a finitely sized accretion disk, which is guaranteed to precess. No one, in principle, accretion disks would be very large, and very large accretion disks cannot precess, so you will need some process to tear off like an inner precessing accretion disk from a larger disk. So this is, I think, pretty substantial that it really works in GRMHD. And yes, also there is lots of interesting jet dynamics. The jet slams into everything. It slams into the outer disk. Now if you look a little bit further in the movie, it will slam in the outer disk and push this outer disk outwards by injecting energy and angular momentum, which is pretty exciting, I think. During my fellowship here, I'm going to extend these simulations by not only getting like qualitative results, but also quantitative results. Why does this disk steer? Besides saying that the lens-fearing torque is bigger than the viscous torque holding the disk together, our understanding is not better than that. What determines it? For example, what role does the magnetic field topology play? Also, I'm already pretty far with including radiation in my code to understand how the interaction of an radiation field with, for example, the outer accretion disk will change the dynamics. Question 2 is also, we have, besides highly tilted disks, even if the disk is not tilted, there is some big questions. Black hole, X-ray binaries transition through different states, which differ by many orders of magnitude in luminosity. And AGN may do the same, only on time scales that are outside of our lifespan. And the question that I want to answer is, how does this transition between luminous and non-luminous disk happen? What processes play a role? And so on. For example, I've run a simulation where I wanted to have a highly luminous accretion disk, which is thin, and this is this outer disk here, but in the middle part actually something interesting happened. I started with a very strong magnetic field, which actually this very strong magnetic field caused the material to fall in so rapidly that if I had included the proper physics, not if I've included some kind of not so good cooling function, but if I would have included two temperature dynamics and proper radiation, then this inner part could physically never be a thin accretion disk, and it would be much thicker and less luminous than this picture actually suggests, and that's what I'm looking at. And for that, I'm already running simulations on Summit. This is, for example, a very high resolution simulation that I'm running this time with a toroidal field. And the bottom line is, from the first highly tilted disk, that the dynamics with a toroidal field seem to be different. The disk doesn't tear so efficiently, which is actually pretty exciting. So here is my conclusion slide with the short conclusions of this presentation. Yes. Yes.
sources. And are you planning on any particular system that LIGO observes?
Yes, I'm now, let's say I'm now also leading an effort together with some graduate students to simulate a binary merger, I mean the post-merger evolution of a black hole and a neutron star under the same ground on this machine. It should be like running in 1 month. So, but there are, of course, we need to have more, let's say, not more, but other kinds of physics included to do that. Yes, Richard? Or
Yeah, I was wondering about the connection between these very nice calculations and observations, let's say at X-ray wavelengths, which we now make, in our own galaxy and many others.
Yes.
So you're simulating this over some period of time.
Yes.
And I'm wondering if in some cases you actually either can see that you'll end up in an end state which is long-lasting and maybe most likely to be observed, or whether you cycle between states and that has implications for the distribution of properties that we would observe in a accreting black hole.
Yes, all of these simulations are pretty short. I mean, on the scale of X-ray, of a 10 solar mass X-ray binary, I think what I showed would be like 10 seconds. I plan to go to a minute. And of course, all of these, for example, these state transitions, they may be driven by just fluctuations in the mass accretion rate from a binary partner. And I mean, that's outside of the reach. That's something that we cannot like simulate. But I mean, we can, of course, let's say, enforce some oscillation and see what happens, for example, for a thin accretion disk. Does the magnetic field that when you kind of cool the disk and it launch a jet in an intermediate state between the hard and the soft state, will this jet last, or will this magnetic field leak out and will the jet shut down? That's definitely something we want to do.
So you can get insight.
We can, I think we can get really, with the time scales and with some tuning, we can get insights I hope really to get insights in what drives these state transitions for sure.
Yeah,
Yes.
it's certainly very important to increase the dynamical range in space with techniques like AMR.
Yes.
But I'm wondering, based on some processes that have very different time scales that are all important for building up, let's say, a jet current, let's say, dynamo current building on an accretion time of years that ends up building jet current that lasts 100 million years in an AGN. Is there any technique or any hope for bridging the large range in dynamical timescales?
Yes, I'm already thinking about it. It may sound a little bit sketchy, but the idea would be, and that would be like a big project, don't expect like something like the next 4 years. That would be to use machine learning to run many simulations, let's say at the scale of 10 RG, then feed the results in at 400 RG, and then kind of with machine learning maybe. But I mean, it's very difficult to do, and there are I think there will be lots of pessimists with that approach, me, myself, so it's definitely something to think about, or to dream about, yes, but hopefully we will be extending it, yes.
Okay, we need to move on. Let's thank Matt.
Good. Yes.
I'll get this done. Yeah. Oh, there you go. Yep, this is good. Okay, so we're going to change gears completely now, and I feel that this is a report of the work that I've been doing here for the past 6 years that nobody knows about. So ACCESS is a survey that basically stands for the Arizona CFA Católica and recently Carnegie, Exoplanet Spectroscopy Survey. It has 3 co-PIs, including myself and Daniela Pai and Andres Jordan from University of Arizona and Católica in Chile. We have had 5 graduate students so far. You recognize the first 2, Ian and Chima, who are students here. Nestor Espinosa, who is now a Gruber Fellow at the Max Planck, and Ben Rackham, who started 2 days ago as a 51 PEG Fellow at the MIT, were our 2 first grad students. And then James Kirk just arrived a year ago, and then we have all these external collaborators as well. So what does Access do? What is the purpose of Access? The idea of Access is to generate the largest uniform observational database of optical transmission spectra of planets over a wide range of parameters. And the purpose of this is to try to answer some of the like standing questions about exoplanet atmospheres. The technique that we use is transits. Some of you have seen this, but many of you probably have not. So briefly, what we do is we use transiting planets for this. So basically, when the planet goes in front of the star, part of the light from the star goes through the atmosphere of the planet, and we look at that light, and we spread it into the spectrum, and we see anything that is going on in the atmosphere. We see molecules that interact with the solar light. We see clouds that block the solar light. We see hazes. So this is the technique. Why observations in the optical are key, we think? So there has been a lot of talk about doing observations over a wide range of parameters, over a wide range of wavelengths, all the way out to 28 microns. And that's what JWST is going to do. HST is doing right now up to 1.7 microns here. So you see that it sees these features that correspond to water. And then JWST can go down to 0.6 microns all the way up to 28 microns. But as you see in these 3 examples here, the data in what we call the infrared, everything redder than 1 micron, could be degenerate in many cases. So if you don't have the information in the optical, you don't know what's going on. The best example is at the very top. You can have a hazy atmosphere in the exoplanet, or you can have a clear atmosphere. And if you only had data redder than 1.5 microns, you could never tell. And once you start getting data into the optical, then you can tell what the difference is in those features. So this is one of the reasons why observations in the optical are so important. Another case is if you have clouds, you can differentiate some of the features in the infrared, but usually the error bars in those observations are pretty large. But if you extend the observations all the way in the optical, then all of a sudden you can tell if what you are seeing in the planet is clouds, or if it is a planet with low metallicity in general, like in different molecules. And the same case here. You can differentiate, you can basically have 3 planets with different amounts of metals in the atmosphere. And if you don't have the optical, you have no idea where that baseline is. So as soon as you put the optical observations in, you can tell which one of those features you're seeing. So this is why observations in the optical are key. For targets, for access, in terms of how many targets, I don't intend for you to look at all these values in this table, but I wanted to show you that we are doing over 40 targets. The ones in the top are super-Earth and sub-Neptunes and Neptunes. The ones in the middle are Saturns, and the ones at the bottom are Jupiters. And they cover a wide range of parameters. As I said, we have planets all the way from 6 Earth masses to 10 Jupiter masses, radii from 2.6 Earth radii all the way up to 2 Jupiter radii, effective temperatures from 700 Kelvin to 3000 Kelvin, and a variety of orbital separations and irradiation levels from 10,000 to 10 to the 9 times irradiation that we get on Earth. And this is irradiation coming from the host star. In terms of stars, we have all the way from M dwarfs to stars more massive than the Sun, and the metallicities of the stars cover a wide range of parameters. So in principle, if we can do all this, we can try to put all the pieces of the puzzle together. One of the biggest puzzles right now in exoplanets is there is clouds everywhere. which I don't know why people are surprised, because if you look at the planets in the solar system, there's clouds everywhere, but we don't understand why. So with all this information, we hope to provide an answer to what parameters are playing a role in planets with more or less clouds and so on. That's one of the things that we're trying to do. To do all these observations, we are using IMAX on the Bada Magellan Telescope. The Time Assignation Committee has given us lots of time, about 5 to 6 nights per year, which is about 10 to 12 transits, but I'll show you that later. And what we are doing is we're using multi-object spectroscopy. IMAX on Bada is wonderful for this because it has a field of view of 27 arc minutes. So we can basically put a slit in the target and get a spectrum. And at the same time, we can put the slits in as many comparison stars that are available in that field of view. And we can remove all the effects from our own atmosphere. And that's how we reach the precision that we need to see the atmospheres of the planets. I'll go briefly through this. This is sort of the observing strategy. We usually get assigned 4 to 5 hours time windows on a given night. The tag is super flexible for us. I mean, they really work around us. We are limited to air masses of less than 1.6 to 1.7 in air mass. And that's just because of refraction effects in our own atmosphere. The information about the grating is just to say that we have a resolution of about 1,000. And then this is the key thing here. This is what nobody had done in the past. We do not publish. At least we have 3 or 4 transits that are consistent. Like we don't just take one spectrum and say, this planet has potassium in it, and just publish it. Like we have to have 3 or more observations showing the same signals. So this is why this project takes a while. What I'm going to, at the very top is just a brief summary of what we have done. We have been doing these observations since the end of 2013. That's about 6 years ago. As I said, we get 10 to 12 transits per year. So it takes a while to build 3 to 4 transits per target. And, but we have it down to about 3 or 4 targets. So we hope that in the next 2 to 3 semesters, we will be able to complete the survey. And now, in the remaining of the time, I'm going to show you 4 examples of results that we already have. This is probably one of the most important ones. A lot of you are probably familiar now with this problem of spots in the star, the spectrum of the spot contaminating the spectrum of the planet. So you have no idea if the features that you are seeing from water or other chemical or other molecules are coming from activity on the star itself, or they're coming from the planet, from the planet's atmosphere. 2 years ago, nobody was talking about this. This was the first result, and this result came out from Access. Ben Rackham published it. We observed the super-Earth GJ1214b, 4 different transits, and in the 4 transits, these are the Access observations, we noticed that the transmission spectrum was going down, and there was no way that we could explain this. So after a while, and furthermore, because of HST data, that in green there, that's Laura Kreiber's data, and Spitzer data, we knew that this planet, this spectrum was probably just flat. So it took more than a year to get this figured out, but it turned out that what we figured out is that what we were seeing here was a spectrum of spots in the star. This star is an M dwarf, so they usually have fairly large spots. And if you have a spot, which is basically a region of the star with a different temperature, what you have is 2 spectra combined. So the star is not only 1 spectrum, it's 2. So that difference, when you subtract the star, if you don't account for this, all the residuals that you have are coming from the star. This is now a very well-known problem. And everybody who does any kind of work on transmission spectroscopy has to apply a correction for the contamination of the spots. The second result that we have, this actually was ready to publish in 2017, but it took us another year because there was another claim for the same planet saying that they were seeing titanium oxide. So basically, WASP, I will finish here. WASP 19 is a Saturn And you see, the reason why I wanted to highlight this result is because you see the precision of the light curves that we get. This is better than HST. So you can see that from the ground, we actually get data that is better than HST. And what we see, the blue points, the green points here are HST. The white points here are our data. We don't see titanium oxide. We basically see a fully flat spectrum. So I wanted to show Ian and Chima that work on this project, but I don't have time. And but so basically, sorry guys, what we can do with Access, the future of Access is we can do follow-up of probably not the little planets, but anything that is a sub-Neptune or a super-Earth and bigger from tests. We can do the observations in the optical. And obviously, the biggest deal here is that we can do all the observations in the optical for JWST. Because otherwise, the solutions from the JWST, a lot of them are going to be degenerate. So thank you to the TAG for giving us all this time. And I will stop here to take questions. Thank you.
Actually, I have two questions. One is resolution of 1,000 enough to resolve the lines? You said 1,000, right?
Yeah, you do. Yeah, I mean, obviously, okay, so I'm going to show, I don't know if I have a good example here. But yeah, so you basically can see the peaks of sodium, potassium, anything that is a molecule that here would be, so here you see, right? It's like you basically, like anything that is like that, you get a couple points. So you can, I mean, obviously it's not as precise as high resolution, but yeah, and you get the slopes in the optical, which are the key to actually determine if you have clouds or hazes. That information in the optical sets the baseline for what pressure you are seeing in the atmosphere of the planet. And so anything that you see in the infrared is going to be, the baseline is going to come from the optical. So you can place much better constraints in abundances and things like that. So.
Okay, and then my second question is, will you be able, so you'll be able to also observe the features from the molecules or just the baseline?
The molecules, yeah.
The molecules are just in the ion.
Yeah, no, the molecules are easier actually. Like you basically see here, okay, so this would be, oh my God, I can't. Okay, so that's a band there, right? So you see that we have 1, 2, 3, 4, 5 points in a band. So the molecules are easier because you kind of trace a shape.
So which molecules?
So for this type of planets, the molecules in the optical are basically titanium oxide. We have a hint, but we are triple checking that solution. We have a hint of carbon monoxide here, but we are really being super careful. And then everything else in the optical is really atoms, like sodium, potassium. So it's basically the titanium oxide, maybe some carbon monoxide, but we're not 100% sure. Yeah.
Okay, let's
Thank you.
All right. Can you hear me? Good. Okay. Let's get the spectra out of the way. Oops, sorry. Go ahead. All right. Hello. Ooh, spinning wheel. Great. My name is Erin Kara. I am your new neighbor at MIT. I just started a faculty position there. And so actually I live much closer to CFA, so on very cold days, you may see me here instead of cycling all the way to MIT. Yeah, so I am here to give the CFA colloquium, and a lot of my work that I'll describe in that talk is about accreting black holes and studying the innermost regions using X-ray reverberation mapping. So using light echoes to kind of map out what those innermost regions look like in accreting black hole systems. So if you're interested in that, I encourage you to come to the talk this afternoon. But today I want to tell you about this really bizarre AGN system that is just like what I'm working on a lot right now, and it's the thing that like gets me up in the morning. And I'll say this is a work in progress, so you're getting a lot of fresh ideas. This is work together with Benny Trachtenbrot, Yair Arkavi, Claudio Ricci, and many people in the NICER Observatory Science Working Group. Okay, so back in March of 2018, the Assassin All-Sky Optical Transient Finder found this bright flare of a well-known Seyfert Galaxy 1ES 1927. And you can see this is the long-term light curve. It had lots of upper limits in the optical. And then all of a sudden on March 28th, we see this bright flare. And in the optical, it continues to decay. This kind of a light curve, perhaps to some of you, is like ringing bells that you see. This is the nucleus of this galaxy didn't have, wasn't very bright, and then all of a sudden you see a flare and this decay over time. Oftentimes, this is a telltale sign for a tidal disruption event. But what do we know about this galaxy to start with? This is, as I said, a well-known AGN. So if we look back in the archival data of this AGN, it's already a kind of peculiar object. So in the optical, it was classified as a type 2 Seyfert galaxy because it didn't have any broad bomber lines, no broad H alpha or H beta. And this in the unified picture of AGN must, suggests that you're seeing this galaxy more from edge on and you don't have a view of the innermost regions. But when we looked in the X-rays in these archival observations, there's no hints of obscuration. This is an unobscured AGN. And you see that this is just a typical Seyfert type 1 spectrum with a power law that extends into the hard X-rays, a gamma photon index of roughly 2 power law, pretty bog standard type 1 AGN in the X-rays with no obscuration. So that was kind of an already interesting thing about this AGN. Then in March, there was this trigger from Assassin, and my collaborators, Yair Arkavi and Benny Trachtenbrot, started getting optical follow-up. And the cool thing about this is that you can see this is the archival observation that I showed you on the previous slide. A blue continuum is the first thing that we see to observe. And as we go up in time, you see the development of these broad bomber lines. And so this is what we think is the first, this is clearly a changing look AGN in that the bomber lines changed. And yet I think we believe that this is the first time that we're actually watching this process happening in real time. And what's cool is that the lag that you see here is consistent with what you'd expect from the radius luminosity relation that you get from optical reverberation mapping. So I encourage you to look at Benny's paper that's already been published for more on the optical spectra. But let's go back. I've been focusing mostly on the X-ray observations. Let's go back to this archival observation from 2011, this bog standard type 1 AGN with the hard X-ray emission that's pretty typical of a type 1 AGN. When we got new follow-up observations with NICER and with XMM Newton, this is what we found instead. So a totally different spectrum, more than 2 order of magnitude decrease in the hard X-rays, and what we're left with is just pretty much this like thermal spectrum in the X-rays. So something has happened, this hard X-ray emission that presumably comes from the innermost regions, this corona we call it, that seems to be ubiquitous in AGN, has disappeared in this object. And it's associated with this flare in the optical. So this is kind of the first puzzle. Where did the hard X-rays go if they are supposed to exist always in AGN? And we kept on monitoring this source with NICER. And so I should just take a moment to say that NICER is this amazing instrument on the International Space Station. And you can, the band that we're looking at is in X-rays with NICER. And it has very good flexible scheduling, and like Swift, it can take observations, every day, but with 20 times the number of counts as you get with Swift. So it's a pretty powerful instrument. So these gray points that you see are what we observed with NICER, and so we were tracking it for a few, 50 days or so, and we were seeing there's lots of day-to-day variability, like over an order of magnitude change day-to-day, but the overall trend was that, like the optical and UV, was that it was decreasing in flux, kind of what you would expect from a tidal disruption event as well. Then, a little bit later, we noticed that it just started to rise again. And this is the spread that you see in the gray points with NICER. Those aren't error bars. Those are actual changes, 2 orders of magnitude day to day. It's kind of blowing my mind. That's much more than you expect from a typical AGN. And we followed up with also some later epochs, the green and the blue, with XMM and New Star observations. And so what you see is that, again, the spectrum looks very different, and now it looks like as this source flux is recovering, or even much brighter, now the hard X-ray emission is coming back. It's not just a normalization change; it's really the hard X-rays are coming back with a vengeance. This is now the brightest AGN. Currently, it has become the brightest AGN in the soft X-ray sky. And that's kind of cool that it's a transient event. Or maybe it'll stay like that. We don't know. We're continuing to monitor this guy. So how do we explain this disappearance of the hard X-ray and the reemergence of the hard X-rays? Okay, I'll just point out, this is when you put everything together. The UV and the optical continue to decrease. We've put this suggestive t to the minus 5/3 dependence with flux, which is what you'd expect from the fallback rate of stellar material in a tidal disruption event. But at that same time, you see that the X-rays have decreased and then increased by 4 orders of magnitude, all while the Balmer lines evolve over time. So how do we explain this curious behavior in this AGN? I'm going to say that I'm proposing one solution here. I don't think that this is a unique solution. I would love to hear your ideas. But what if we are seeing a tidal disruption event that has occurred in a radiatively efficient, standard AGN disk? And, this is possible. You might expect, just based on, galactic dynamics, that whatever is triggering the AGN activity would also cause more stars to enter the loss cone. And so perhaps it's not crazy to think that you should get some tidal disruption events happening even in radiatively efficient AGN. So let's say a star comes in. This is a disk system that's emitting in the UV, optical, and you have your compact corona that's producing this ubiquitous hard X-ray emission. A tidal disruption event occurs, causes some instability in the accretion disk. The magnetic fields that were presumably threading the disk and creating the heating mechanism for the corona, perhaps this tidal disruption event is enough to disrupt that magnetic field configuration, destroy the corona. And now as we watch this system evolve over time, we're seeing this hard X-ray emission kind of restabilizing. And just to say, this was also kind of backed up, this idea is backed up by recent GRMHD simulations from Chan et al., Svi Paran and Julian Krolik's group. And what they found was that you can have a stellar debris depending on the mass ratio or the mass accretion ratio of this stellar debris and the accretion rate onto this black hole. This can be enough, this stellar disruption event can be enough to kind of change the disk configuration on these kinds of timescales. And they predict that you would see stream shocks due to the collision of this debris stream with the accretion disk. And I'm suggesting that I think there's one last hint that may kind of tie this all together. Maybe there's hints of this stellar debris stream hitting the accretion disk in the X-ray spectra that we see. If you fit this X-ray spectrum here with a black body component, a thermal component, this feature here is way sharper than the Wien tail. And when you fit the continuum, what you see is there's emission at around 1 keV, very broad, which may be evidence for collisionally ionized plasma, possibly due to these stream-stream collisions or stream-disk collisions. So that's it, and I'll take any questions you have. Thanks. Right.
And not actually disrupt the stars. So
Yeah.
you want this black hole not to be more massive than, a few times 10 to the 7 solar
Absolutely.
masses. Now,
It is. It's 10 to the
what
7.
is the estimate?
10 to the 7. And we've got pretty good constraints on that because of the bomber lines and the delay that you see. Yeah.
And in that case, the disruption occurs at about 10, less than 10 torches by, like very close to the
Yeah.
black hole. So the X-rays need to be emitted very close to
Yeah. Actually, that's a really great point. That's another kind of indication that this X-ray emission that we're seeing, is coming from a compact region, which we've kind of known. We've known this from just kind of normal AGN, but if this is the right picture, then it confirms this compact corona. Yeah.
Any other questions? Yes, go ahead.
Since you asked for other ideas,
Yeah. This is great.
I don't know really anything about this system, but if you had a binary at the center, and it's been shown in simulations of circumbinary disks that accretion is sort of episodic, like it'll build up at the cavity edge and then all fall onto it at once. So you could imagine. I haven't thought about whether the whole picture would get tied together,
Yeah.
but you could imagine the emission then comes from different places at different times. As it sort of lands on the mini disks, and so you may maybe think about whether, I don't know whether that's a possibility.
Yeah. I would like to think about that possibility more. What is more crazy? What's the is it a tidal disruption event happening in an AGN or a really close nearby supermassive black hole binary system that's gone into outburst?
I hope there's lots of really close supermassive.
Yeah. Or a tidal disruption event happening in a supermassive black hole binary.
Well, the issue with that, with the binary, is that the X-rays will not disappear. You need some obscuring material.
I see.
Well, but it's clearly not an obscuration event that's hiding the X-rays, because you still see you see all of that soft X-ray emission, and if it was just obscuration, you shouldn't expect to see the soft X-ray emission either. So that's really, I think, telling us that the corona has turned off, somehow.
Well, we need to move on. Let's stay.
Thank you.
Okay, mic check, working? Excellent. All right. So, as I'm sure you all know, research can often be a very messy process. And it's not often you get to tell a straightforward story with a clear beginning, middle, and end. And luckily today, I get to tell one of those stories. This story started during my thesis work at graduate school and ended here at the CFA, working with the Conroy group. And I didn't always used to do galaxy SED fitting. When I started my thesis, I actually had a very different plan. In 2012, we had just finished making these very deep, very complete catalogs of galaxies across the majority of cosmic time. And our plan at the time was to simply write down the solution to galaxy evolution directly from the observations. And by solution, I mean how galaxies grow in mass. The plan was to not use any simulations, not even use the word halo. We were going to scoop all you illustrious folks. And it was a good plan. But unfortunately, it was doomed. And this is why this plot has sort of driven the last 4 years of my research. And so here, this is a plot of the star formation rate density. And those two purple lines are measuring the star formation rate density in two different ways. One is by watching the observed mass growth of galaxies, and then inferring how much star formation should be happening. That's the lower one here. And the other one is from observing the instantaneous star formation rate. How many stars are forming at the exact time of observation. These two things should agree. They're measured independently. They're measured from largely independent parts of the electromagnetic spectrum. And they don't agree. They don't agree by a factor of 2. This is a big problem. This means that there are systematic errors of at least a factor of 2 in the way we infer these quantities in galaxy SED fitting. So I know we're all astronomers here. A factor of 2, maybe not a big deal. But I can assure you, and I don't have time to get into it in this short talk, that a factor of 2 is a really big problem for galaxy evolution. Okay, this causes all sorts of issues, especially for people who try to do modeling. You can't fit the observations when the observations themselves are internally inconsistent. Okay, so we set out to try and fix this. And the first question is, why? What's going on? Why is this broken? Why is this such a hard problem? And the problem, in essence, is that these galaxy SED models, they have many different ingredients, and they're all important. Okay, so I'm going to show you a little table here. On one side is some parameter, which is important in galaxy SED fitting. And the other side is sort of the order of magnitude hand-wavy effect on the SED. This goes on, of course. I truncated it for time. I haven't mentioned anything from stellar population synthesis. I haven't mentioned anything like magnetic fields. So this is why this is a hard problem. There's a lot of ingredients, and they're all important to the process. Okay? And so for each of these ingredients, you have to make some decision. And everyone can make very different but reasonable decisions and get very different answers as a result. So this is what's going on here. And so to try and address this, in the Conroy group, we've been using this code called Prospector. It was originally written by Ben Johnson here at the CFA. And so this little movie is just showing Prospector doing its thing. Here I've generated some fake SED with fake properties over here. And we're fitting it with Prospector and adding in 1 or 2 bands of photometry at a time. So we start off with just 1 band of optical photometry. We progress to a color. We add UV, near infrared, far infrared. And over here, you can watch these parameters sort of start very unconstrained and then one by one march towards the truth here. And so there's a lot going on in this movie, and I encourage you not to stare at it too much because you'll sort of lose the forest through the trees. But broadly speaking, what we've done here is try to build a model that can constrain many parameters at once, and it doesn't overfit. Okay? And so we eventually converge to the right answer, but when given not enough information, we don't get the wrong answer. Okay? This is sort of the goal of this project. And this has been an ongoing project for a long time. We've done a lot of validation work with this, sort of fitting observations and then trying to predict other observations to check how well we're doing. And I won't talk about a lot of that work here today. I'm going to jump right to the punchline. After a couple of years of working on this code, we took it and we went back, and I mentioned earlier how we had these deep, complete catalogs of galaxies. We went ahead and fit them with this code. Okay? So this is the 3D HST candles photometric catalogs. They have some 30, 40 bands of deep rest frame, UV to mid-infrared photometry, plus accurate redshifts for a massive number of galaxies across the majority of cosmic time. It's a fantastic data set. And we took our code and we fit most of it. I say most of it because the code is relatively slow. So the spitting process took about 1.5 million CPU hours. We couldn't have gotten it done without the majesty of the Odyssey computing cluster here. Okay, but once we went through this process, we could take the things that we got out and look back and sort of say, have we made any progress on this problem? Does this change anything that we've been seeing before? So what we did was we took the outputs and we compared to the previous sort of state-of-the-art SED fitting codes. And previously, SED fitting codes, they would have like a handful of parameters, maybe 4 or 5. You can get a little bit farther. Sort of the more recent codes will have sort of 9 or 10 parameters, but they'll be very baked into the code. For a lot of technical reasons, there's not a lot of freedom in these things. So with this sort of new, very free model, it takes a while to run, we asked, what changes? The first thing that changed is we actually find substantially more massive galaxies. And so this offset in mass on the y-axis increases as you go to lower masses. And so whenever you see something like this, the first question is why? What's going on? And there's a lot of knobs in this model. In principle, this could have been a very complicated question. But in practice, it was actually very straightforward. Here's 3 different things that might have been causing this difference. Different masses on the y-axis, that's the offset between ours and the original, and then a bunch of different measurements on the x-axis. Turns out, very straightforward, we find much older galaxies than other SED fitting codes by a factor of 3 to 5. So this is a big difference. The next question we should ask is, given this difference, is this a reasonable difference to find, or are we sort of barking up the wrong tree here? And so this is something we looked into quite a bit. And I'll just sort of sketch the argument here. We sort of stack the implied star formation histories for these galaxies and ask, does this make sense given what we know about galaxy evolution? So here, this is sort of the classical approach using these declining tau models. Here, these are the prospector star formation histories. And I'll point out that this is a log axis. So any differences you see are much bigger than they appear. Okay? And so if you take the previous star formation histories at face value, these are measured at about redshift 0.75. But if you take them as they are, they imply that there were 0 galaxies in the universe 3 gigayears ago. And this is when the universe had an age of 7 gigayears. Okay, so these aren't a very realistic solution if you take them at face value. If you actually take the prospector ones and you can wind back galaxies through time and ask, can you reproduce things like the galaxy stellar mass function, you do a fairly good job. So these ages are probably much more reliable. This was a big confidence boost. The other piece of the argument, star formation rates. Prospector infers these lower star formation rates. Okay, so again, this is the offset on the y-axis as a function of this, in this case, specific star formation rate, which is star formation rate over mass. We find good agreement for galaxies that have a lot of star formation going on. But as there's less and less star formation, we find an increasing offset down. And this offset actually becomes pretty dramatic out here for these more quiescent galaxies. Almost a full order of magnitude, we infer lower star formation rates. So here we're comparing to these UV plus IR star formation rates. Okay. And again, the solution could in principle be very complicated. In practice, it's pretty straightforward. Most of this effect is coming from this heating from old stars. So when you measure a star formation rate normally, you assume that all of the UV and all of the infrared luminosity is generated by very young stars. And from that, you can back out the number of young stars and the star formation rate. In actuality, this is not true. When I say young stars, I mean anything younger than 100 megayears. There are many stars older than 100 megayears in galaxies. And it turns out they also emit, both in the UV, and they heat the dust, which is then re-emitted in the infrared. So when you do all this self-consistently, you find that this energy from old stars is a big deal. And it lowers the star formation rates of galaxies by quite a bit. And this effect is sort of paradoxically stronger at higher redshift, because at this point, old stars were relatively younger and more luminous. And so we can go back to this plot I showed at the start of the talk, where we had this sort of systematic offset between these 2 measurements of galaxy growth, and say, okay, we spent all this work rebuilding everything from scratch. Does it change this picture? And it does. Actually, there's excellent agreement now. And so this was a really happy moment for us, because we had built this SED fitter with no eye towards changing this plot in any specific way, just trying to fix things that we thought needed to be improved. And so to have this outcome come out like this and have it agree self-consistently and also be significantly different from the consensus here by something like 0.2 dex was really a wonderful thing to say. And that's the end. Yeah, so that's part of the thing is you get a different row star as well using this methodology. So sort of everything changes. There's not a standard comparison to compare with at this point. So the next step in this project, which is alluded to down here, is to go back and sort of remeasure everything with this code and see if the answer is self-consistent. That includes measuring the mass function, integrating it to get the stellar density, comparing it to the inferred star formation rate. So that work is ongoing. It looks promising.
What do you think the Baruzzi of image-matching models are on?
So the Baruzzi models, of course, they only fit to the observations. And so they're only good insofar as the observations are internally self-consistent. Peter Baruzzi actually pulls a trick, which I think is very cool. He fits a nuisance parameter that says, I'm just going to assume that observers have no idea how to measure these things, and that there's some systematic offset between the star formation rates and the stellar masses. So that's just a parameter in his model. And that offset comes out to be about 0.3 dex, and it's about in the right direction. So I think the models work by construction because he assumes the observers are wrong, which is something I happen to agree with. I mean, that's an excellent question. It's one I wonder about all the time. I think, in some sense, adjusting things until everything is self-consistent is the process of science. You're right. We have no ground truth to compare with. We have nothing that we can go out and say, hey, this is absolutely correct. And I think in the absence of this ground truth, all you can do is sort of build increasingly more self-consistent models. And you can also try and be very careful about testing your answers. So a lot of the slides I left out here, due to time, are me going out and saying, okay, I'm going to fit the photometry of this galaxy and then try to predict the spectrum. I'm going to fit the photometry of this galaxy and try to infer whether there's an AGN in there, and then test it with external data. And I think that's sort of the best way we found to go forward in this process, is to use better, more detailed data as an external check on how well our models are doing. Thank you.
Okay, well, let's thank all our speakers today. And we are going out to get photos.
That's
Great.
Thanks. Great.
Don't walk off with it.
Classic. Yeah.
I did that when I gave it to him.
It's such a convenient
Yeah.